This is the second of 3 videos on nuclear reactions, and here are the teaks that we're covering. From the first of our installments, we realized that scientists discovered that certain elements are giving off radiation. Alpha radiation, which are helium ions, beta radiation, which are electrons, and gamma radiation, which constitutes high-energy, low-wavelength light. Scientists wanted to know why this is happening and how it is happening. They know that there are several kinds of atoms, different in kind. They have the same chemical behavior, but differing masses, and they're called isotopes. Some isotopes are stable. They're low energy. They don't give off radiation. The most common isotope of carbon, carbon-12, is such an isotope. Some isotopes, though, are not stable. They give off radiation. One example is called radiocarbon, carbon-14. This isotope is used to find the age of objects that contain carbon, because as time goes on, the amount of carbon-14 is reduced. Some of it is going away. You can see this carbon-14 trace as time goes on, and again this is measured in years, the amount of carbon-14 remaining compared with its original 100%. We trace that in a kind of a logarithmic decay. The graph shows how much carbon-14 remains after a certain number of years. Other tests show that nitrogen-14, which is the next element in the periodic table, it has one more proton, has taken the place of the carbon-14. Carbon-14 then has turned into nitrogen-14 by giving off a beta particle, that is, by losing an electron. Now, if we balance the equation, we can write the decay process, and we use the shorthand that everyone has agreed upon. It's called a nuclear equation because it's not a chemical equation. It's showing changes in the nucleus itself. And here's the equation for the decay of carbon-14 into nitrogen-14 and an electron. As you can see, as always, the mass is on top and the atomic number is on the bottom. The 14 mass number appears in the nitrogen, and as we know, the electron has essentially no mass. But now, since the electron has a -1 charge, we see that to balance the equation, we have increased the atomic number from 6 to 7, and the beta particle has taken away the negative charge that made that change. So how to write a nuclear decay equation? You start off with what you know is decaying, and on the right side of the arrow, what it decays into. You write the starting reactants, the nucleus, on the left, and then you write a right-facing arrow, and then you write the decay product or products. You make certain that the numbers on top, that's the mass, equals. Left equals right. Then you make certain that the numbers on the bottom, that's the charge on the nucleus, that those numbers are equal on both sides. And you manipulate the numbers so they match. So you can add fundamental particles, alpha particles or beta particles, usually on the right side of the equation, so that we get good balance on the top and on the bottom. For example, a radium isotope of a mass 222 gives off an alpha particle. What new isotope is produced? So you start with the only reactant, radium-222. It has 88 protons. You write the arrow showing the decay. You add the known product, which is an alpha particle, which has a mass of 4 and a charge of 2. and you determine what the top and bottom numbers on the other product must be by subtraction. This is equal to this number plus whatever number on top on the decay product, and 88 is going to be equal to this number plus whatever the decay product has on the bottom. Of course, the numbers on top are 218 and on the bottom 86. We then look up the product on the periodic table. The bottom number tells us the atomic number, and we find that it is radon. Radium is decayed into a helium nucleus, an alpha particle, and radon-218. You do one. Iodine-131 decays by giving off an electron and gamma radiation. What isotope is also given off? And the hint is the gamma radiation has no charge and no mass. It is pure energy. So turn off the video and solve the problem, and then come back and check your answer. The answer, of course, is 131, since there's no mass on the other products. 131 mass, and 54 charge because the electron is taken away, a -1. Beta decay changes the charge and the element identification, and therefore its chemical properties, but the mass is not changed in a beta decay. Here are the two types of common nuclear decay that actually change the nucleus: alpha decay, beta decay. The particle given off, the change in the charge, and the change in the mass. This would be a useful table for you to memorize.